This is experiment 6, determination of calcium. We know calcium in limestone, which is calcium tricarbonate 4. So the first thing you're expected to do is weigh 2 to 3 grams of the sample, which is calcium tricarbonate 4. Once you've done that, you're expected to grind the sample to fine powder. So you'll be grinding to fine powder. Then you take some portion, let's say you take 0.2 gram of the fine powdered 2 to 3 gram calcium tricarbonate 4. So once you've taken it, now you would add this weight amount, all right, in a given volume of HCl. Let's say you had HCl, the required volume is in your manual. So let's say this is a beaker and then some volume of HCl is in it, right? So you would add that weight portion. Let's say you took 0.2 gram of the calcium tricarbonate 4, right? You add it here. So once you've added it, definitely there's going to be a reaction between the calcium carbonate and the hydrochloric acid. So this reaction is just calcium tricarbonate 4, right, reacting with HCl, which should give you calcium chloride plus water plus CO2. Carbon dioxide is evolved. So once you've added this, you have to warm. Once you've added the calcium carbonate into the HCl, given volume, all right, this reaction happens. Now effervescence will be observed, which is due to carbon dioxide being released. So once you've observed that the effervescence of the carbon dioxide have stopped, then you would now introduce the oxalic acid. All right, you'll be giving some of this is the oxalic acid. Remember, we had the first reaction. Please, this is going to be equation 1. Let's write it. Calcium tricarbonate 4 reacting with HCl to give CaCl2 plus H2O plus CO2, which is evolved, right? So the next thing you're supposed to do is you dissolve a given amount, all right? The weight amount is going to be in your manual, all right? You dissolve that given amount of oxalic acid, H2C2O4, all right? You dissolve this in a given volume of water. You're just going to dissolve it in water, distilled water. So you're dissolving this in a given volume of water. Now, what you want to do is that you want to precipitate the calcium from the calcium chloride, right? Because this is a soluble form of calcium, right? So now you're going to add this mixture that you've dissolved of the oxalic acid into this particular system, right? Into equation 1, into this the reaction vessel containing this effervescence, all right? So once you've added this, another reaction will happen. Remember, this is giving off, this is water, so this is going to react with the calcium chloride. So we're going to have the oxalic acid, right, reacting with CaCl2. Now, what you're going to have here is calcium oxalate, CaC2O4 plus hydrogen chloride. All right, you can see. Let's check if it's balanced. These two hydrogen, I should have 2 here. So I should have plus 2 HCl. All right, 2 chlorine, CaC2O4. Can you see that this balanced? So this is our equation 1, this is our equation 2. Now, look very well. This actually means that 1 mole of calcium carbonate requires 1 mole of the oxalic acid, or 1 mole of the oxalate. So essentially, it is 1:1. All right. So because this is essentially what we need. So what we are going to do to this is that we are going to now heat this system. All right. We're going to heat it to 80 degrees Celsius. Once you've added the oxalic acid measured amount that has been dissolved in water, add it to the previous reaction. All right, this is going to happen. This is the reaction that is going to take place. Okay, So once that is done, you have to heat this system again to about 80 degrees Celsius. Add methyl orange indicator. Do you know why you're adding the methyl orange indicator? We have an acid, right? We have an acid. What we want to do is, we are not interested in the hydrochloric acid. We want to neutralize this so that we'll have essentially this. Remember, we have calcium. We don't need this. Okay, we're going to add methyl orange indicator, right? And then we're going to introduce a base, an ammonium hydroxide solution, because ammonium hydroxide is a base, right? Hydrochloric acid is an acid, right? So once we've added it, a neutralization reaction occurs. So HCl is neutralized, leaving us with this. And that is why we're adding methyl orange. So once you've added the methyl orange, the system, the color will be pink. All right, you get to observe that the color is pink. So, but then, once we introduce this, you observe the pink color, right? Now we are going to now introduce ammonium hydroxide solution. Right? We're going to introduce ammonium hydroxide solution to the system again. And remember, we want this to react with this. So the indicator is going to give us the endpoints to which hydrochloric acid has been released, has been neutralized. So once you're adding this, you have to be adding it gradually till this pink color, all right, changes to orange. You observe an orange coloration. So once that is done, we are sure that hydrochloric acid has been neutralized, meaning that it will not interfere with our species here, which is our analyte. This is our analyte. This is what we're interested in, and this is what we want to determine the amount of calcium in limestone. And remember, 1 mole of calcium carbonate is giving 1 mole of the oxalate, right? So now, this is essentially it. Let me wipe this off, okay? So we are going to filter the solution. You know, we're going to have the solution, right? So we're going to filter. Let me draw something like this. Let me have a filter funnel. Alright, so we're going to filter. So we'll collect whatever that we've gotten from this product, neutralization, all the reactions so far which have been happening. So we're going to introduce it into, we're going to filter, right? So remember, you put your filter paper on. So once you filtered, all right, we're going to have the filtrate here. This is the filtrate, right? This is the filtrate. Remember, we want this. So the calcium oxalate is going to be on the filter paper. That is the filtrant, or it's going to serve as our residue. So we're going to have essentially CaC2O4 on the filter paper. While we expected to have the hydrochloric acid that has reacted with the ammonium hydroxide. You know, let me show you this. Ammonium hydroxide reacting with HCl is going to give us ammonium chloride plus water, right? Salt and water. This is very soluble. Ammonium chloride is very soluble, so it's going to come out as the filtrate. You collect it here, all right? So what you're going to do is, to the filtrate, you're going to test if there are some presence of chloride ion. Essentially, we want a positive test. We want to detect for the presence of chloride ion here, so that we'll be sure that we've collected the ammonium chloride which has been removed to separate, to get us this, right? So we're going to test that, take some portions, test it with silver nitrate. Silver nitrate can react with chlorine to give you a white precipitate, precipitating silver chloride, all right? So essentially that's what we want to do. So once we've gotten a positive test to ascertain for the presence of chloride ions in the filtrate, all right, then we are sure that what we have on the filter paper is essentially our calcium oxalate, which we're interested in the calcium. So what then happens is that we're going to wash this down, all right? This still, now we can actually do it here, or you can just, you know, bring out the filter paper. Be careful so that you don't lose any mass, all right? Then you puncture the filter paper, all right? Use the still water in a separate beaker this time around, all right? In a separate beaker, all right? once you've punctured the filter paper, in a separate beaker, use distilled water, wash down this precipitate, all right, of the calcium oxalate completely. Ensure that everything goes in here. So this is what we need, right? So once we've collected this is essentially going to be CaC2O4. And remember, this is having a direct relationship with the calcium carbonate, all right? Because this is coming from the calcium carbonate. 1 mole is to 1 mole, all right? So once you've got to this stage, the next thing you're going to do is, remember we have this, right? So the next thing you are going to do, please don't forget this equation 1 and 2. I'll refer back to them later on. So the next thing we are going to do is, we are going to add sulfuric acid. We want to acidify the calcium oxalate. That means we're going to have CaC2O4 plus H2SO4. Please, the given volume will be there. So we're going to have this and this reacting. Definitely we have a calcium sulfate, right? Plus the oxalate is precipitated. Can you see that? So we're going to have essentially this. Once you've acidified it, you're expected to warm. You warm the mixture, all right? You have to warm it. Don't boil it. Warm it and titrate against potassium permanganate. All right? Potassium permanganate will be in the burette, more like trying to serve as our acid in our acid-base titration, okay? So it's going to be in the burette. Remember, potassium permanganate is an oxidizing agent, right? The oxalate is reducing agent, okay? And remember what we said. The oxalate is directly equivalent to the calcium carbonate, all right? Because we derive the oxalate from the calcium carbonate by reacting with the oxalic acid. Remember in the first stage, okay? So what we have here is, we're going to have in the burette potassium permanganate, then the acidified solution of the oxalate, right? We're going to pipette it. So based on the volume of pipette you're given, just pipette some given amount, introduce it into the conical flask, right? You don't need an indicator because this system is purple, is colored, okay? So I'm not going to tell you the observations, so you have to be observant to see what color and what color is being, changing. All right, so once you've gotten your endpoint, that is going to give you the volume of the permanganate used. In this case, we are after the volume of the permanganate. All right, so and the permanganate is in front. This is a redox reaction. So let me just write the equation of reaction. Then from there, I would try to use a simple value to illustrate how you are going to calculate the whole thing. Now, if you look at your manual, I think you were asked to find the moles of the manganate ion, all right? Percentage of calcium in the mixture. So these are what you are required to deduce from this experiment. You have to know the equation of reaction. So we are having, this is the equation of reaction, the redox reaction, okay? If you observe closely, there's a reduction of the manganese ion from this to this, all right? But from what oxidation state to what oxidation state? That is not what I'm after. But then we can actually calculate this. This is from here to here. This is +2 oxidation state. What is the oxidation state of manganese here? So how do you do that? This is X plus 4 minus 2 equals to -1. So you have X minus 8 equals to -1. So you have X equals to -1 plus 7, which is what? -1 plus 8, which is what? Plus 7. So there is a reduction from 7 to 2. All right. So if one chemical species is reducing, the other is oxidizing. So you can find that out. So interestingly, this is what I'm after, okay? So now from your data, I'm trying to use, trying to devise some values so to guide you in all your calculation. So now let's say, for example, the concentration of the, definitely, we need the concentration, right? Because you are standardizing the burettes, which contain the potassium permanganate, is of known concentration. So let's say the concentration of the potassium permanganate, right? The concentration was given to be 0.01 molar, all right? Let's assume this was the concentration that you were given, all right? And then let's also assume that the volume of the permanganate, all right, once you run your titer values, the average, I'm talking about the average now. This is the average. More like when you have VA, all right? Volume of acid required to neutralize, right? So now that is what I'm trying to refer you to as. So let's say this volume was actually given to be 24. Let's say you got 24 cm cube as average value, okay? And now let's also assume that the volume of the pipette, which you pipetted the oxalate, right? Let me write 204 2 minus. Let's assume that you made use of a 25 cm cube pipette, right? Which you pipetted, right? And in an acid-base reaction, this is equivalent to our VB, right? See that, right? So now let's also tend to assume that, okay, should we make any other assumption? Please, these are likely data you're supposed to have, all right? I'm just trying to give you an example. Let's say you've carried this out and you got this as your volume of permanganate. So how would you actually calculate, the moles of permanganate ion, which is MnO4? Remember, concentration of volume is given. All right, so I'm going to give you guys an insight. Now look at this reaction. If you look closely here, 2 moles of the permanganate, right? 2 moles of the permanganate, which we introduced into the burette, required 5 moles of the oxalate, all right, which we introduced into the conical flask. Look at it. Can you see this? This is 2 moles is to 5 moles. Now what I'm going to do is I'm going to wipe this off. All right, you can see that on the screen to continue from where I start. So looking at this reaction, 2 moles of permanganate, which we introduced into the burette, required 5 moles of the oxalate, right? So I'm just going to write C2O4 2 minus, right? So now remember, we know the concentration of this. This is our standard solution, okay? But we're interested in the oxalate because the oxalate will give us an insight about calcium. Remember, from equation 1 and equation 2, if you remember, equation 1 had to do with CaCO3 essentially precipitating H2CO4 in the second equation. This is from the first equation, this is from the second equation, and it was 1:1 mole. All right, so that means this oxalate is significant to telling us the calcium. All right, so now, which is also, remember we had this CaC2O4 from previous reaction, you will still say this, so they are all equivalent, okay, because we essentially introduced this into the sample. All right, so having that in mind, now look at it very well. You have to know this relationship, that number of moles, we'll get back to this, okay? Number of moles is volume, all right, times concentration. Now you see, so we can actually know the what's it called, the number of moles here for the permanganate, all right, but we don't know how much. This is just giving us the ratio 2:5, but we want to quantify it. All right, so number of moles of manganate of the permanganate ion is going to be what? The volume. What volume did you get from the reaction? The average titer value that we talked about. Remember, I gave 24, right? So it's going to be 24, right? 0.00. Remember, we are dealing in concentration. This is per dm cube. So since it's per dm cube, this volume, I'm dividing it by 1000, then multiplying it by the concentration, which I said, let's assume we were given 0.01. All right, mole per dm cube. Can you see that? So from here, you can actually get the number of moles, which is part of what you expected to calculate. All right, so this is essentially how you do it to get the number of moles. Remember, this is cm cube, this is cm cube, right? This is going to be 0.12324 moles. Remember, number of moles, right? Can you see that? So this is the what the value with what I'm showing you with the value we just assumed to have been derived from the experiment. So this is how you essentially go about calculating the number of moles due to the permanganate ion. All right, you see that? So that is the number of moles. So how would you now calculate the number of moles for the oxalate? Now, if you want to calculate the moles of the oxalate, that is essentially equivalent to the moles of the calcium carbonate, because this oxalate was precipitated from the calcium carbonate, going from equation 1 through equation 2, just have said earlier. So I'm going to wipe this off. Remember this value. So remember, my moles of permanganate, I derived 0.12324 moles. So how much is this going to be? All right, and what we're going to get here is due to the moles of calcium carbonate, because they're equivalent if you go by the equation 1 and 2 and the previous equations, right, that I've just shown you. Okay, now what we essentially do here is 5 times this. All right, it's going to be 0.12324 multiplied by 5. X times 2 is 2x. So I'm dividing both sides by 2 by 2. So whatever this gives me, let's say this times this, let me see what's going to give us. That's 0.1236 moles in this case. All right, so this is the number of moles of what? Calcium carbonate. Calcium tricarbonate 4. So this is how you go about calculating this. If you want to calculate the mass of calcium, right, having arrived to this, you've gotten the number of moles. So what is the mass of calcium? I'm going to wipe this off just to guide and show how you can go about that. Remember, number of moles is given mass over molar mass, right? So you've derived 0.2306 moles, right? So how do they essentially get the mass of calcium? That is calcium specific. Calcium is 40, molar mass of calcium is 40. So we have number of moles, which is what? 0.1236 will be equal to how much? Always going to be the mass of calcium divided by molar mass of calcium is 40. So essentially we're going to have that value, all right, multiplied by 40, which should give you around 0.024 gram. Can you see that? You see how we used the number of moles of calcium carbonate to derive the the mass of calcium, right? So we essentially get something like this. Remember, you should know what your value is giving you. This is an example. It's not telling you this is exactly what you're going to be getting. No way, right? So how would you calculate the percentage of calcium in the mixture? All right, in the mixture. How much did you weigh? How much did you weigh in the first instance? That is what it's trying to ask you. So let's say you weighed, you ground 2 to 3 grams of calcium carbonate. Then you took some portion, and let's say that portion you took was 0.2 gram. So this is what you're getting, right? So the percentage of calcium is going to be this value, 0.024, divided by how much you weighed before adding HCl, those reactions started. Let's say it was actually 0.2, and if you multiply that, that will give you the percentage of mixture. But in this case, I should be having 12%, all right? So you see, this is essentially how you go about the experiment and calculating the amount of calcium in limestone, which is calcium tricarbonate 4. So try to note this and know exactly, follow this up, take these things down and follow them to understand them better. It's better off you understand than just writing or copying.